Today we're going to be talking about section 3.4. We're actually going to end up spending a couple days on this section, and what I think you're going to notice is that a lot of what we're talking about here relates very closely to what you've probably learned about before in your physics classes. So what I'd like to do is start by going over some basic vocabulary so that when we start saying these words, you understand the notation and the meaning behind these words in a math class. Let's start with position. The position function for an object moving along a line, for example, say the x-axis, describes the location of an object at any given time. So a lot of times in this class we're going to deal with there's a particle sliding along a line. It's just sort of going back and forth and back and forth. It's sliding left and right and left and right. How do we know where the particle is at any given time? The symbol for position function is s of t. We always use the letter s for position because p was already taken. We used that for momentum. For example, a dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of s equals 160t minus t 16t squared after t seconds. How high does the rock go? If we're trying to figure out how high, this is really asking us about the highest spot. Now, if we think about a parabola with a negative leading coefficient, we know that a parabola is going to be downward facing, so we're trying to find the spot that's at the top of that mountain. In order to figure out the highest spot, we need to look at the maximum, or the place where the derivative equals 0. So to solve this problem, we would first start by taking the derivative of our position function. The derivative would be equal to 160 minus 32t. Now we want to know where our derivative equals 0 because that's going to be the place where there's a maximum or a minimum. So we would have negative 32t equals negative 160, which if we divide gives us 5. So, at t equals 5 seconds, the rock reaches a maximum. Have we actually decided how high it goes? Well, no, we know when it reaches the maximum, but we don't know how high it actually goes. To figure that out, we're going to need to find the position at 5, because that will tell us how high we actually go. So I'm going to get out my calculator, and let's see here. 160 times 5 minus 16 times 25, which is 400. So 400 feet is the highest this rock will go. Okay, next, displacement. Displacement of an object describes how far away an object is from where it started. There are two different ways to calculate displacement. The way that I prefer, the way that I think is the easiest way to calculate displacement, is to take your final position minus your initial position. So I'm using F to represent final and S to represent initial. A dynamite blast propels a heavy object straight up with the same launch velocity, the same position function. At t equals 4 seconds, how far away am I from where I started? This is asking me, if I'm saying from where I started, it's asking me about displacement. So to calculate my displacement, I'm going to need my position at the end, which is at 4, minus my position at the beginning, which in this case would be 0. S of 4 would be, 160 times 4 minus 16 times 4 squared, which would be 384. So 384 minus my position at 0 would be 0. So I am 384 feet away from where I started. Now, one of the benefits of position is that position is a vector. So position tells us direction. Displacement tells us direction. So the nice thing about displacement is that it tells us the direction. If my displacement is positive, then that means I am 384 feet to the right of where I started. If my displacement was negative, I would be 384 feet to the left of where I started. The sign of your answer here tells you which direction you were traveling in. Okay, next vocabulary word we need to know. Average velocity. We've been talking a lot about instantaneous rate of change, which is a derivative. So it's very important that we know the difference between an average velocity and an instantaneous velocity. Average velocity is given over a specific time interval, and it describes the average rate of change of the object. For this, we're going to use regular old slope. Now, velocity can be positive or negative. It just depends on which direction you're traveling in. Velocity is again a vector, so it tells me how fast I'm going and the direction I'm traveling in. Now, if you think about velocity as a slope, velocity would be the slope of position. So to calculate velocity, you would do your final position minus your initial position divided by your final time minus your initial time. Another way that some people think about it is delta S, the change in your position, divided by delta T, the change in your time. But either way, it's just slope. Y2 minus Y1, X2 minus X1. So, same situation, dynamite blast, blah, blah, blah. What is the average velocity over this interval? We would need to calculate S of 3 minus S of 0 divided by 3 minus 0. So, S of 3, 160 times 3 minus 16 times 3 squared, which is 9. So 336 minus my position at 0 is 0 divided by 3. So I would get 112 feet per second. Now you'll notice that this is positive. So that means that I'm traveling to the right or I'm moving up. If it was negative, that would mean that I'm traveling left or down. Kind of like on a graph. So to the right and up are positive, to the left and down are negative. Now, what's the difference between average velocity and instantaneous velocity? Instantaneous velocity is the slope or the derivative of the position function. Remember, instantaneous always means take a derivative. So we would look at velocity, which we call a brand new function v, is the slope of position. When we're talking about a v function, this is always instantaneous velocity. We would never use v of t to represent an average velocity function because you can't really write a function for that. You would have to take each individual interval separately. So, same situation, blah, blah, blah. What is the velocity of the rock when it is exactly 256 feet above the ground on the way up? The first thing I know is if I want the velocity at a specific time, I need a velocity function, which would just be the derivative of position. So it would be 160 minus 32t. But in order to calculate this, I need t. In the problem, instead of telling me the time, it tells me the position. I can use that information to figure out the time. So to figure out time, G-U-R-E, we want to know when our position, which is 160t minus 16t squared, is equal to 256, because that would mean that I'm 256 feet above the ground. If I move everything to one side, I'm going to have 0 equals 16t squared minus 160t plus 256. Now if I factor out a 16, I would have t squared minus 10t plus 16 equals 0, which factors to be t minus 8 and t minus 2. So my two different times when I would be 256 feet above the ground are at 8 seconds and 2 seconds. Now remember, we're traveling in a parabola. So I'm going to hit 256 on the way up and on the way down. The earlier time has to be the way up, and the later time has to be the way down. Now that I know I'm concerned about when t equals 2, I would say, okay, what is my velocity at 2? I would get 160 minus 32 times 2, which is 96 feet per second. All of this stuff right here was because I didn't know my time. So I had to kind of do some extra work to figure that out. Okay. Moving right versus moving left. When we're talking about which direction we're moving in, we need to look at the velocity function and the sign, more specifically the sign of that function. When velocity is positive, I'm going right. When velocity is negative, I'm going left. So, if I have the same situation and I want to know when am I moving to the right and when am I moving left, the first step for one of these problems is always to find the velocity function. In this case, I would just take my derivative of position, so 160 minus 32t. The second step is to make your velocity function equal to 0. Now you might be wondering, why would I make it equal to 0? Because this is a parabola, there's going to be a certain time when the velocity stops at the top of the curve. This is going to be the place where velocity changes from right to left. Once we know where our velocity changes, we can section off the velocity into whether it's going right or left. So if I solve this, I should just get 5, which I had done in a previous problem. The third and the last step is to make a chart. We need to look at the sign of our velocity function. The beginning of our time is 0. You can't really have a negative time. We know that something happens at 5. And after that, our object just kind of moves to infinity. What I'm doing here is I'm basically making a number line starting at 0, and I'm using this value to put numbers in the number line. If there was more than one spot where the velocity equals 0, I would have more than one marking in the number line. Now what I'm going to do is look at the sign in these sections. If I pick a number between 0 and 5, like 4, and I plug it into this function, I'm going to have 160 minus 128. 160 minus 128 is definitely a positive number, so I would be moving to the right. If I pick a number between 5 and infinity, like 6, 6 times 32 is over 180. So if I plug that in, I'm going to get a negative number, which means I'm moving left. Here's what I can say. I can say that I'm moving right between 0 and 5. I can say that I'm moving left between 5 and infinity. And I could even say that I was stopped at t equals 5. Again, I'm giving intervals here because there are entire sections, entire chunks of time when I'm doing this kind of motion, when I'm traveling to the right or traveling to the left. Next, we're going to look at speed. The speed of an object is the absolute value of the velocity. For speed, we're just looking at how fast we're going. We're not looking at the direction we're traveling in. So, speed is the absolute value of your velocity function. For example, if I say what is the speed of this same rock at t equals 2, first I would take the derivative and get my velocity function, 160 minus 32t. Then I would calculate the velocity at 2, which is 160 minus 64, so 96. Then I would say speed is the absolute value of that number, which in this case would stay the same. If my velocity had originally been negative, then my speed would have been the same number but positive. Last but not least, we're going to look at acceleration. So we've looked at position, we've looked at velocity and some stuff we can do with velocity. Now we're looking at acceleration. The acceleration of an object describes how fast the velocity is changing. Is your speed, your velocity, how fast you're going, getting faster, or is it getting slower? Therefore, if we want to know how fast velocity is changing, we just take the derivative of velocity. Now, just as a heads up, on Earth, if we're ever measuring in feet, you're always going to have gravity is 16t squared, and gravity would be negative 9.8 t squared, so you would start with 4.9, just sort of to remind you. So acceleration is the derivative of velocity. So if I say in this same problem, what is the acceleration of the rock at t equals 2? First, I would find the velocity, which is just the derivative of position. Then I would find the acceleration function, which would be the second derivative. So do the derivative again. What is the acceleration at 2? Well, in this problem, since there's no place to plug in a number, the acceleration would just be negative 32. And we would say feet per second squared, because acceleration is always measured in per something squareds. Last but not least, speeding up or slowing down. The speed increasing or speed decreasing. These all mean the same thing. Speeding up is the same thing as speed increasing. Slowing down is the same thing as speed decreasing. We can tell if an object is speeding up by looking at both the velocity and acceleration functions. A lot of students make a mistake here and think, oh, I can tell if I'm speeding up or slowing down by just looking at acceleration, which is not true. You need to look at velocity and acceleration. If velocity and acceleration have the same sign, then the speed is increasing, or we say that we're speeding up. If velocity and acceleration have opposite signs, then the speed is decreasing, or we say that we're slowing down. So, is the particle speeding up or slowing down at t equals 2? In order to figure that out, I need two pieces of information. The velocity, which I need the function 160 minus 32t for, I'm just taking the derivative, and the acceleration, which again is the second derivative, negative 32. Then I need to figure out those values at 2. The velocity at 2 we figured out before was 96, and the acceleration is 32. We did those in previous problems. Because these have opposite signs, we would say that we are slowing down at t equals 2. Ooh, you can't see what I'm writing. Just kidding. There you go. Because these have opposite signs, we would say that we're slowing down at t equals 2. I know this is a lot of vocabulary. Hopefully some of it is familiar because you've seen it in physics. When you come to class tomorrow, we're going to look at an example of the type of question that I might give you with using this vocabulary. And that's it.